The final type of task that we're going to discuss today is the task of finding out associations between two variables. Just because there are only two variables, this is still called basic statistics. Anything that involves more than two variables will be called multivariate statistics. So far today we've only been discussing tests that involve essentially two variables. Well, if it's dependent measures, technically the number of variables could be larger, but still it's a very basic hypothesis. We took a little bit of look at correlation coefficients before, and we discussed Pearson correlation in pretty much detail. Pearson correlation, you can use it for the situation when you have two variables that are both interval and normally distributed. But of course, you have other types of correlation that you can use for other situations. Most notably, if you can only assume that both of your scales are ordinal, you will use Spearman's rho, which is basically Pearson's correlation, but calculated based on ranks rather than based on your raw data. And for nominal variables, there are also special types of kind of correlation, like Guilford's phi for 2x2 tables, etc. For correlation, I remind you that things are a little bit more easy with effect sizes because the value of correlation coefficient itself is its effect size. And you just need to check out significance level to make sure it's significant and it's not there by chance. And I remind you about the three assumptions of Pearson correlation: that data are normally distributed, the scale is interval, and the association is linear. And these assumptions are normally related. If your data are not interval, if they are ordinal, typically you'll see that the distribution is not normal and the association is not linear. And I remind you that if your Pearson correlation is close to 0, it means that there is no linear association. But this association might be nonlinear, and there are more universal correlation coefficients that try to quantify this situation. In addition to just our normal correlation coefficient, we can also calculate coefficient of determination, which is basically the square of Pearson's correlation, or R squared. And this R squared reflects the proportion of variance that two variables share with one another. This is why it's called coefficient of determination. And this logic of determination, it kind of leads us to regression approach. When we perform a regression analysis, we ask the question whether we can predict the values of one variable based on another variable. The variable that we are trying to predict is called criterion variable, and when we plot it, we normally use vertical axis for this variable y, and the variable that we use to predict is called predictor variable, and we plot it on the axis x, normally on the horizontal axis. So we say that we regress our criterion variable on our predictor variable. However, when we just have two variables, x and y, basically there is not much of a difference between correlation and regression. Essentially, it's the same analysis. And your linear regression will be, the standardized coefficient for your linear regression will be exactly the same as Pearson correlation. But just in order to understand a little bit better this logic of regression, let's take a look at an example of linear regression for two variables. So we have our predictor variable x, which we call for this analysis independent variable, and we have our criterion variable y, which we call for this analysis dependent variable. When we try to develop this prediction, we try to find a linear function that best describes this whole bunch of points. So for each individual point, we have an expected value, which is basically this position on this line for which corresponds to the value of this point on x. So this point on this line would correspond to the predicted value of this point x. But of course, in our real data set, we have the actual value of this data point, an observed value, and this difference that we see between the predicted value that we expect and the observed value that we actually see in our data is called error or residual. And later on, when we discuss regression, we'll pay some attention to those residuals or to those errors. Right now, let's just take a look at the association between correlation and regression. When we try to draw this line which goes through all of these points, we basically try to describe it with a function. And if you remember from secondary school, a linear function is always y equals a plus bx. And these two parameters are called slope and intercept. Slope is basically the angle at which this line goes in relation to horizontal axis. And intercept is the position of this line with respect to vertical axis. So intercept is basically the value of y when x equals 0. And sometimes this value makes sense. Sometimes when your score on x can only go from 1 to 5, obviously this intercept will be substantially meaningless, because your variable x cannot have a score of 0 if it can only take values in the range which doesn't include 0. So sometimes this intercept has no substantive interpretation, but still it is there. And you can calculate also your standard error of prediction, and sometimes you can graphically show the confidence interval for your observations. But so far, let's take a look at those two formulae. The slope of your regression, byx, is equal to your correlation coefficient multiplied by standard deviation of y and divided by standard deviation of x. So essentially, if your standard deviation on both variables would be 1, your regression coefficient would be equal to your correlation coefficient. Or if you standardized both variables, the slope of this line would be exactly equal to your correlation coefficient. And the intercept of this line, a, is mean of y minus this b parameter multiplied by mean of x. So you can always find this intercept if you know two mean scores and if you know the slope. And then again, if both of your variables were standardized, your a parameter would be equal to 0, because mean scores on both variables would be 0. That's why we make this distinction between the unstandardized regression coefficient, which is b, and the standardized regression coefficient, which is called beta. A standardized regression coefficient is basically the coefficient that you would obtain if both of your variables were z-scores. And for two variables, it is exactly equal to your Pearson correlation coefficient. How does this work with real data? Well, for example, this comes from one of the data sets I've been working with. The vertical axis are the evaluations of satisfaction with life using Dinner's satisfaction with life scales, where we have 5 items with response scale coming from 1 to 7. And we just calculate an average score for these 5 items and the average satisfaction with life in our sample is 4.62, and standard deviation is 1.22. But in order to predict this satisfaction with life, we use another variable, which is basically a subjectively evaluated meaning of daily activities. It also has several questions, like the things I do every day are important to me or have value for me, and so on. And the answers on this scale can go from 1 to 5. It's also a Likert scale. And the average for that scale is 3.96. And because it has a smaller number of scale points, the standard deviation is also smaller. It's 0.74. So it's not so large. So if we calculate Pearson correlation between these two variables, R equals 0.47, which is a moderate correlation. And here you see a line which describes the association between two variables, and this confidence interval, 95% confidence interval, calculated based on these theoretical parameters. Now you see that here this distribution appears to be as if cut off. This variable is censored because the response scale ends at 5, but most people give answers in the range between 3 and 5. There are few people who give answers in the range from 1 to 3, suggesting that probably we need to use a larger response scale or less extreme items to kind of capture this variability better. So we have expected values here, but no observed values here. So if we want to calculate expected satisfaction with life based on meaning of daily activities, we would need to calculate those regression parameters, intercept A and slope B. And in order to calculate this slope, we would need to multiply our correlation coefficient by the ratio of these two standard deviations. And the result we would get would be 0.80. And it's here calculated automatically by the software package Statistica that I used for this graph. And the intercept we can also calculate if we know two means and if we know this slope. So it's basically this. And this intercept A, it equals 1.45. So if we want to actually predict satisfaction with life based on the meaning of daily activities, we would need to multiply this raw score for meaning by 0.799 and add 1.45. But of course, these exact numbers, they don't really have much substantive meaning because they depend on the scale in which this variable is measured. So this slope or unstandardized regression coefficient, it depends on how many response points are on this scale. And if it was from 1 to 7, for example, it may have been smaller, not 0.8, but maybe 0.5 or something. And this intercept, again, it also has no substantive meaning because it corresponds to life satisfaction given the meaning of daily activities of 0. But 0 does not exist even on our response scale, and it's not even drawn on this graph. So if our meaning of daily activities could be 0, this is the satisfaction with life that we would get. So these raw parameters are not very important. That's why when we report our results, we don't really pay much attention to them, because in psychology our scales are always different and it's a matter of convenience and convention. But what we are interested in here is standardized regression coefficient, which is not dependent on scale. And this beta coefficient, standardized regression coefficient that we would obtain if we standardized both variables, for just two variables, it's equal to correlation coefficient. That's why when we want to present an association between two variables, a correlation coefficient is completely enough to describe how strongly they are related and to explain how we can predict one variable from another. So if we square it, the R squared would be something like 0.22, which would mean that the meaning of daily activities and satisfaction with life share about 22% of variance. But of course, there are other um, causes of individual differences in satisfaction with life, right? How much money you have, where do you live, in a nice neighborhood or in a lousy neighborhood, and so on, in a large apartment or in a small apartment. So all these variables, if we included them in the equation, could explain additional variance. That's why 22% of common variance, it's not maybe not very much, but it's not little. It's quite a substantial proportion, given that given how many things life satisfaction depends on. And again, if we only have a pair of variables, then correlation coefficient is enough to describe this association. Now, what happens if our data are non-normal, if our data are, for example, ordinal? Let's take a look at this situation. We have different types of correlation coefficients. Most often we use Spearman correlation coefficient, which is basically Pearson correlation calculated for ranks. So it's less powerful in case of normally distributed data because it loses some information. But it's more precise in case of abnormal distributions. There are also other options. There is a Kendall correlation, which is not convenient because it's not in the range from -1 to 1, so it's almost never used in psychology nowadays. And for special cases, there are also tetrachoric or polychoric correlations. They are basically generalizations of Spearman correlation, but they assume that the scale underlying the variable is continuous. That's why polychoric correlations are often used in the context of test development, because they produce more precise estimates for correlations between different Likert scales when you assume that there is a continuous property which is quantified by this Likert scale. But in SPSS, polychoric correlation is not given, but in R you can calculate it easily or in other packages. And also you can use a nonlinear regression approach. Instead of trying to generally calculate this association, you can have more specific expectations about the shape of association between two variables. And then you can use a custom nonlinear regression function. And for nominal variables, the question of association and the question of difference between the groups is the same question. So there you use cross-tabulation and you quantify the association between two variables using some measures like Guilford's phi and so on. So just to use an extreme example, let's take a look at those two variables. Clearly non-normally distributed, life expectancy in different countries, and gross domestic product adjusted for purchasing power for these countries. So obviously not normal distributions, and in economics this is often the case. So what happens if we look at this scatter plot? Clearly this association is probably not linear. It looks more like a hyperbolic, inverted hyperbolic function, and there is a strange country which is probably an outlier. I don't know which country or territory it is. So if you want to get an idea of how to model your data, it's best to inspect your scatter plots, and then you can choose the right approach. But even if you don't choose any approach, you can just calculate those two correlations in SPSS, Pearson correlation and Spearman raw correlation. And you see that here Pearson's correlation is 0.55. Fairly substantial. If we square it, it kind of captures something like 30% of variance between two. It suggests that the shared variance of two variables is about 30%. However, if you look at Spearman correlation, it's much stronger. It's 0.79 almost. And it suggests that over 60% of shared variance is common to these two variables. So a Spearman correlation coefficient does much better job of capturing this association. So if you see a situation like this, when Spearman correlation is stronger than a Pearson correlation, it suggests that the association between two variables is monotonous. One variable is increasing, the other one is also increasing, but it's nonlinear. It may have a different shape. And for this situation, Spearman's correlation is much more optimal. However, if the association is perfectly linear and both distributions are normal, then Pearson correlation might be slightly stronger because it uses more information from the data. But of course, you can also make other assumptions about the shape of this association. For example, in SPSS, you can use nonlinear regression in analyzed regression curve estimation, and you can basically tell SPSS what kind of functions do you want to use in order to predict life expectancy based on GDP across countries. And you can order different functions. You can order, for example, a linear function and a linear regression where we know how to calculate these parameters. Here, this slope is just basically too small, so it was rounded to 0 because the GDP is expressed in thousands of dollars and life expectancy is just expressed in years. If you want to have a more tangible value here, you probably need to rescale one of the variables. But R squared here we can see is 0.30, which means that a linear function only captures 30% of shared variance. But other functions, they capture other percentages of variance. For example, a quadratic function is a little bit better. It's 41% of shared variance. And there is an equation for this quadratic function. And logarithmic function is still a little bit better. It captures about 51% of variance common to both variables. So if you look visually at the graph produced by SPSS, you see that a linear function shown with the complete line kind of does a fairly bad job at capturing these two variables. Quadratic function, which is this one, fares slightly better, but logarithmic function is the best. And this is the reason why logarithmic function, so yeah, this is quadratic function, inverted parabole, and this is logarithmic function, line point, line point. So this is why logarithmic function is often used to model this type of data, or you can simply apply a logarithmic transformation to this predictor variable GDP, and then linear function will be equally good to capture this association. This is how you deal with nonlinear associations, and we'll explore also other ways of using regression to model them in case if these associations are more complex. A frequently asked question that people ask, what about binary variables? For example, if you have an outcome on exam, success or failure, or gender, male versus female, if you have these binary variables, can you calculate correlations? Well, in principle, these variables officially are nominal. But because they are binary, the special types of correlations that you would use for these variables are exactly the same as Pearson correlation. If one of these variables is nominal and another one is quantitative, for example, correlation between gender and exam score, this point biserial correlation is equal to Pearson correlation. So you can basically calculate normal Pearson correlation and get the result. Or if one variable is ordinal and another one is interval, then this biserial correlation is rank biserial is a special case of Spearman correlation. Yeah, so you can safely use a Spearman row. However, if your dichotomy is artificial, you created it by dichotomizing some kind of interval variable, then the estimate will be biased, and it's a bad idea to apply a correlation like this. Then you would need a tetrachoric or polychoric correlation to quantify this. Yeah, so when you're interested in correlations, normally we choose between Pearson R and Spearman Rho, but there are also special cases like polychoric correlation that are useful in special situation. And if you have regression for two variables, it's exactly the same as Pearson correlation. Some people don't know it, and they publish Pearson correlation, and here is a regression of y on x. But come on, it's completely redundant. Yeah, so this is a little bit of excursion into regression. I hope you have got the difference between the unstandardized and standardized regression coefficient, because this is what we are going to use later on when we take a look at multiple regression with several predictors. This distinction will be important. But for today, our discussion of basic statistics is over. Let's just spend a little bit of time on two special questions. How do we present our data? And how do we deal with missing data? But those bits are completely optional.